All right, folks, we are back, and now we're going to be studying discriminant functions, the first approach to doing this classification problem. So let's get into it. All right, so a discriminant is a function that takes an input vector, x and assigns it to one of k classes denoted C of k. Okay, so you put in your input, your image, and it's going to tell you what animal it's got by putting it into one of the classes. In this chapter, we shall restrict attention to linear discriminants, namely those for which the decision surfaces are hyperplanes. And we'll talk about what all of that means. To simplify the discussion, we consider first the case of two classes, and then investigate the extension of the case greater than two classes. Okay, so let's highlight linear discriminants. And those are the ones for which decision surfaces are hyperplanes. All right, so let's start with the two classes. The simplest representation of a linear discriminant function is obtained by taking a linear function of the input vector so that y of x is just this. Okay, so that's what we're going to be talking about. Where w is called the weight vector, so good terminology. And let me highlight this guy. And w naught is a bias, and yeah, so just some terminology. This doesn't mean like a bias in a statistical sense where your estimator is off from the true value by some amount. It just means like you can think of it like as a threshold, basically, a threshold for for exciting this particular unit. The negative of this bias is sometimes called a threshold. Threshold, right? Or you can think of it as like its value, its activity when the input is 0. An input vector x is assigned to class C1 if y of x is greater than 0, and to class C2 otherwise. Okay, so that's how it works. So it's kind of a binary. You can think of that binary, that f function we talked about in the chapter overview, as being this binary, as a step function basically. The corresponding decision boundary is therefore defined by the relation y of x is equal to 0, right? Because on one side you're going to put it in class 2, on the other side you're going to put it in class 1. Which corresponds to a d-1 dimensional hyperplane within the d-dimensional input space. And the reason, we talked about this, but again, you have this d-dimensional input space, so your weights are going to be d-dimensional, and your x's are going to be d-dimensional, and then you're going to look for the set where y of x is equal to 0, and that's going to give you one constraint. It's just a scalar, scalar value of your inputs, and so then that's going to leave you, d-1 degrees of freedom. So that's one way of thinking about it. Another way of thinking about it, maybe it's a little bit more intuitive in some sense. You can think, okay, well, if you know d-1 of the values of x, then the fact that y of x is equal to 0 tells you the dth value, right? You have to set it so that the dth value is what it is, and that's going to define so you have actually d-1 variables there, not d. Okay. So the corresponding decision boundary is therefore defined by the relation y of x equals to 0. So this is going to be really important because equations like this are going to be important because they're going to define decision boundaries. So you're going to get good at dealing with them. d-1 dimensional hyperplane within the d-dimensional input space. Okay, great. Now consider 2 points, x of a and x of b, both of which lie on the decision surface. Because y of xa is equal to y of xb, we have that, so you just subtract, that wt times the difference is 0. And hence the vector w is orthogonal to every vector lying within the decision surface. Because if you remember your equations for hyperplanes, from wherever you learned it in analytic geometry, whatever it is, w is going to be perpendicular to that surface, and the reason why is this: that if you take any 2 points on that surface, then w is going to be perpendicular to the line that connects them. So let's just do that. And so w determines the orientation of the decision surface. Similarly, if x is a point on the decision surface, then yx equal to 0, and so the normal distance from the origin to the surface is given by, okay, so yeah, we're going to go and look at a figure, so if this doesn't make much sense to you right now, but what we're doing is, so what we're going to determine that distance, we're going to need to project x onto w and normalized by the length of w. And because we have our equation that says y of x is equal to 0, that tells us that wtx is equal to minus w naught. And that's why you've got these two on either side of the equal sign. So the bias parameter, it kind of tells you where the location of the decision surface. If w naught was 0, then that surface would go through the origin and it'd be oriented in a particular way. And then as you increase w naught, then that surface then actually starts receding backwards. We therefore see that the bias parameter determines the location of the decision surface. These properties are illustrated for the case of d equals 2 in figure 4.1. So let's go have a look at this figure, and let me just make sure you guys can see it, because I think it's a very, yeah, great, you can see it. Okay, cool. So let's see what we have here, right? So we've got, so here's the origin, so let's just put a big O there. Okay, good. And so here's your W, so your weight vector, and here is some point. So now you want to figure out how far along, you know, what, and this is, sorry, and this is the y equals to 0 decision surface. And now you want to figure out, well, what decision surface is, you know, what value of, essentially, how far is x from the origin? Well, the way you do that is you project x onto this point, right? So this is going to be w hat tx times w hat, right? So w hat tx gives you the length, and then you project out along that location. So this length is w hat tx, and which is basically what we have on this side. And now we want to say, well, what value does that actually have? And it turns out that, you know, from the relation of the decision surface, we can determine that it actually has to equal w naught over the size of w. So this, and the size of w is showing up just because you need to normalize by that size when you're doing all of these projections. Okay, so yeah, and then we'll come back to this figure. Yeah, here is this minus w naught over w. Yeah, right. So this is, yeah, this was on the surface. Let's see what he wants to say. So the reason why he's highlighted that is because this is the surface where wtx, was it minus or plus? Right, plus w naught is equal to 0. And so all of the points on this particular surface, they're going to satisfy wtx is equal to minus w naught. And so wtx over, which is going to be the length of all of these points. So every single point, we do this exact same thing. We try to figure out, well, how far is it, what is this projection onto this weight vector? You can think of it as, like, you know, as kind of contour lines. Which contour line are they on? Well, all of the points on here are all going to be on the contour line minus w naught divided by the norm of w. So the kind of this bias term kind of just tells you where the, you know, how the decision surface moves. So for, you know, when w naught is positive, then the minus w is going to move things backwards, and kind of indicates that, okay, you need to have some negative excitation of y to actually get a 0 value, and so on. Okay, so that's just some of the geometry of it. It's kind of very useful to keep in mind and be kind of comfortable with that. Okay. Furthermore, we note that the value of y of x gives a signed measure of the perpendicular distance r of the point x from the decision surface. So, you know, we were talking about, we were just talking about the set where y of x equal to 0, but now, well, what if it's non-zero? So it says it gives a signed measure of the perpendicular distance r of the point x from the decision surface. Okay, so let's highlight that. It's a very cool property. Okay, so to see this, consider an arbitrary point. So let me delete all this. Oops, let me erase all this before it gets too crazy. Okay. So to see this, consider an arbitrary point x and let x perpendicular be its orthogonal projection onto the decision surface. Okay, so there's x perpendicular there. Okay, so now we say, well, x itself is going to be x perpendicular, so this point, plus some unknown value times w over w prime, and this is the same as r times w hat, right? So this is just, you're going to be going some value, some, let me use a different color. It's going to be x dot, and then you're going to go up r times w hat, which is what this is. So now we need to figure out what r is. So multiplying both sides of this result by w transpose and adding w naught and making use of y of x is this relation, and that y of x prime is x perpendicular to 0 because that's on the decision surface. We get that r is going to equal to y of x divided by the norm of w. So that's pretty cool. So it's kind of like we had this point that, well, everything on the decision surface has a value of 0, and stuff off the decision surface, well, it's just going to have it's going to tell you, how far you are once you normalize by the norm of the w vector. Okay, so that's exactly kind of what we have in that figure. Okay. Now he says, as with the linear regression models in chapter 3, it is sometimes convenient to use a more compact notation in which we introduce an additional dummy input value x naught equals 1, and then define w tilde is w naught w. So the bias kind of goes in there, and then x tilde has its value on on that unit as well. So that I think this should actually be, yeah. So yeah, this should actually be 1, right? So that y of x is equal to, remember, so we just had this was supposed to be wt of x plus w naught. Well, if we arrange things in this way, we'll get exactly that. So in this case, the decision surfaces are d-dimensional hyperplanes passing through the origin of the d-1 dimensional expanded input space. So the key idea here is that these guys will now be passing through the origin, whereas before they were kind of shifting around, and the dimensionality's gone up. Passing through the origin of the d plus 1 dimensional expanded input space. But the basic idea is the same. It's just a matter of kind of notation. Sometimes it's a little bit more convenient. Okay. Cool. So I'm just thinking, is there anything else I wanted to say about that particular section? I think that's about it. Yeah, I think it's just, again, I think kind of going back to this point, it's just, you got y of x is going to equal to w transpose of x plus w naught. Well, it's just to figure out the length of how far that x is, you have to just project it onto w and normalize appropriately. So essentially, that's kind of what we're getting here. It's just that we have this constant offset term. So it's not that we can't just interpret this as the distance from the origin. We have to interpret it as the distance from the decision surface. So anyway, something to keep in mind. I would suggest getting comfortable with these geometric pictures because later on they're going to be important for motivating and understanding some of the algorithms that we're going to encounter. Cool. Okay, so I think that is all I want to talk about for that particular section. I think we might as well now just continue on and do 4.12 and talk about multiple classes while we're here. Okay, so now let's consider the extension of linear discriminants to k is greater than 2 classes. Okay, and now this is kind of interesting. The problems that might arise are kind of interesting. So we might be tempted to build a k-class discriminant by combining a number of 2-class discriminant functions. However, this leads to some serious difficulties, as we now show. Okay, consider, so let's just highlight that because yeah, so this is kind of a cool thing, and we'll see why. Consider the use of k-1 classifiers, each of which solves a 2-class problem of separating points in a particular class C of k from points not in that class. So this is can you guys, let me move this over. Okay, so that's basically what we have here. Okay, this is known as the 1 versus rest classifier, and you'll see this. So I think, for example, in scikit-learn, when you want to do multi-class classification, there is this option of, I think, 1 versus rest, if I recall. Certainly somewhere in there, I have seen it. Okay, so the idea, you're going to learn a classifier that's doing just one of your classes versus the rest. It also has, I think, other problems like the classes aren't balanced and things, so you have to deal with that. Like make sure, like imagine if you have 100 classes, and you wanted to do, is it the one versus rest where is it class one or not? Well, like by default, if your data is arranged uniformly, well whatever 99% of it's going to be in the not class, so you're going to get like really good performance, really good performance. If you just don't learn anything and just say no, it's not. So you have to kind of be careful about that. But that's not the kind of issue we're going to be talking about here. So that's what I talked about is kind of a practical issue. There's almost like a kind of a conceptual issue with that whole idea. The left-hand example shows an example involving 3 classes where this approach leads to region of input space. Okay, so this is the key point. It's a region of input space that are ambiguously classified. Okay, so let's see, why are they ambiguously classified? So if we have a look at these guys, what's happening here? So it looks like, so these guys on the one hand are in R1, so they in C1, right? Because they're on this particular side. But then they're also in C2. So you can't, and then there's R3, which is in either one, I suppose. So the question is, these guys are in C1 and C2, which is problematic if you want to do assignment to one or the other class. So that's kind of the ambiguity that's arising. That's one source of ambiguity. An alternative is to introduce k minus 1 over 2 binary discriminant functions, right? And that's because you're going to one for every possible pair of classes, right? So that's where this comes from. There's k, and then you pick k minus 1, and you don't distinguish, x versus y and y versus x are the same classifier. So that's the divided by 2. One for every possible pair of classes. This is known as 1 versus 1 classifier. And you're like, hey, okay, so now each point is then classified according to a majority vote amongst the discriminant functions. And I think I have used this like back in the day on one of the papers. However, this too runs into the problem of ambiguous regions, as illustrated in the right-hand diagram of 4.2. Okay, so now let's go have a look and see like why we're getting ambiguous regions here. So we want to do this majority vote thing. And let me use a different color. Okay, so we're gonna do each of the cases one at a time. Okay, so if you're in there, then we know that C2 is greater than C1. I'm going to say, okay, so the classifier reported that its score was higher for C2 than C1. Okay, so that's for this discrimination. But then it says, okay, well, now, but you're also on this side of this particular class, of that classification. So we also get C3 is greater than C2. Okay, so we can't get so now we can't get a 2. Well, we still could get a 2 majority, but let's see what happens. And now what's the very last one? We see, oh, it's okay. It's on this side of the C1 versus C3 classification. So here we've got C1 is greater than C3. So you don't get a clear winner, right? You've got, it's kind of rock paper scissors situation. So C2 wins once, C3 wins once, and C1 wins once. So there's no majority. How are you going to classify that point? Is it C2? Is it C3? Is it C1? So that's kind of the ambiguity that can arise. Okay. Okay. So what can we do? Well, we can avoid these difficulties by considering a single k-class discriminant comprising k-linear functions of the form so and so. Okay. So considering a single k-class discriminant comprising. Okay, so you see in the idea here, if each of them has its own w and its own offset. And then assigning a point x to the class ck if yk of x is greater than yj of x for all j that is not equal to k. So you can essentially compute this number, and you make the classification to the class that gets the largest excitation. Okay, so let's highlight a few of these things. The decision boundary between class Ck and class Cj is therefore given by yk of x is equal to yj of x, and hence corresponds to a d minus 1 dimensional hyperplane defined by so and so. Right, so that's just coming from, this is coming from the equation for k, this is coming for the equation for yj, and you're taking it to be equal. So you essentially get, you're going to get, I guess, for each, if we hold k fixed, you're going to have k minus 1 of these boundaries, and the points that are going to be classified as wk are the points that are on this, essentially the same side of all of those boundaries. So let me see if I can draw a good picture of that. So let's say like this was the, let's say the k1. So everything here is going to, so all the points on this side are going to be such that yk is greater than y1. So let's do that. So this is like yk is greater than y1. And then let's say there's another class like over here. This was, maybe do a different color. This is, I guess, yk, so it should be on this side, yk is greater than y2. And so now the points in here, so that's the region that's going to have yk being greater than y1 and y2 for all the x's in there. So that's going to be the decision set, the set of points that are going to be classified as belonging to k. If there's, you get the point. So it's going to be kind of the intersection of all of these not half surfaces, like half volumes, whatever they are. Okay, the decision regions of such a discriminant are always singly connected and convex. Okay, so he's going to check convexity first, and if you recall, so convexity just means that if you have a set like this, or any set, basically, you're convex if you take 2 points in a set, every point along that the line joining them is also in the set. So this is an example of a non-convex set, whereas this one is convex. Singly connected, we'll talk about. I think that just is, so on the web, singly connected seems to kind of alias to simply connected. But I think what he means is this. We're going to be able to see that these sets have only one connected component. So you're not going to be in situations where like this is in the decision region, and then this is in the decision region, but the point in between, the points in between aren't. And it looks like convexity should already imply single connectedness, but either way. But that's my reading of singly connected. I don't think there's another definition called which sounds similar, which is simple connectedness, and that's the definition that says that if you take your set, you should be able to shrink every loop to a point. So donuts, for example, aren't allowed. I don't think that's quite what he means. I think he means having a single connected component, essentially just showing that these decision regions are well behaved. Like you're not going to have like this, some corner of the space is, and then some other corners in the region, but then in between there isn't. So it's just showing that it's a well behaved region. Okay, so let's just see how he does that. So consider 2 points x of a and x of b, both of which lie inside the decision region Rk, as illustrated in figure 4.3. Any point x hat that lies on the line intersecting x of a and x of b can be expressed in the form, right? So there's just that's how you express the points in between here and there. So there's x of a, x of b, and some parameter that's kind of taking you from one to the other, and you just vary this between 0 and 1. Now from the linearity of the discriminant function, let me erase all of this. Right, so from the linearity of the discriminant function, so we've got, what's y of k of x hat is y of k of lambda xa plus 1 minus lambda xb, but due to linearity, that is the same as this. Okay, so y of k of x hat is just lambda of y of k at one end plus 1 minus lambda times y of k at the other end. Because both x of a and x of b lie inside that region, the region where y has the largest value for this particular category, it follows that y of k of x of a, y of k x of a is greater than y of j x of a, so when you're comparing two different classes. And the same is true at x of b, so at both the ends. And then therefore it'll also be true for all of the points, along the way as well, right? Because you can just write, you can just apply that exact, for any point along that way. Let's say you're comparing it to y of j of x of hat, and you'll see that the k component is greater, and the component, the component coming from A is greater, and the component coming from B is greater. So you can just check that, and you'll see that the net result will have a larger value for the class K than for the class J. So every point along that set is also going to be inside the region. Hence, and so x of hat lies inside R of K. Thus R of K is singly connected and convex. Well, we've just done a convexity analysis. So if I understand him by what he means by singly connected, you can just see that, okay, well, if we've just shown that you can't have that situation where this is in the region and this is in the region, but there's some gap in between them. So I think convexity implies singly connectedness. So I don't know why he says it twice, but yeah, why he emphasizes that. But maybe he's just trying to say, look, it's just well behaved. Like he's just trying to emphasize. Maybe it's not obvious that single connectedness is something we should be thinking about, and he's just trying to maybe emphasize that. That's how I read it. Okay. And now just kind of a final kind of convenience point. So note that for two classes, we can either employ the formalism discussed here. So just think of it as the K class case, but for just two. So you have two output units, one for each class, or else use a simpler but equivalent formulation described in the previous section where you just have a single discriminant. So for two classes, things are a bit easier. You have some options. All right, so then the next few sections of the chapter are going to be talking about how to actually learn the parameters of this function, this W, and the bias. So there's least squares, Fisher's linear discriminant, and the perceptron. And next time we'll kick things off with least squares, so the first approach. So yeah, I hope you learned something in this section. I actually particularly enjoyed this bit, the ambiguities that can arise. So that was kind of a nice visual description as always. Make sure you are understanding everything that's going on here. It's going to be important, of course, in this chapter, but then later on when we talk about support vector machines, this is going to be important as well. It's just good to have a handle on geometry and how to express it, in symbols. Very good. So I hope, I hope you had fun, and I will see you next time when we talk about least squares for classification. Bye.